So our next topic is very important, very useful. Mean value theorem. In the study of single variable calculus, f is a function continuous in a closed interval and differentiable in the corresponding open interval. Then fb minus fa is the derivative of f at some point in the interval multiplied b minus a. This is called the Lagrange mean value theorem. This is true for single variable functions. And we have known that this is very important in the study of single variable functions. For example, from this theorem, we can deduce that if a function has a positive derivative, then it is an increasing function. If the derivative is identically zero, then this is a constant value function. Okay, so we can obtain the many useful conclusions. So now we are studying multivariable functions. Of course, we need to establish the corresponding result for multivariable functions. This is the content of this section. Okay. So the result is the theorem here. Omega is an open subset, okay, of Rn, and the segment contained in omega, and the f is a differentiable function in omega. I say that f is differentiable means that f is differentiable at every x in omega. The meaning of this function to be differentiable is that it is differentiable at any x in omega. Okay, this is the meaning. So what can we say? Here is an omega, and a segment which endpoint AB, the segment is contained in omega. Then we want to compare the value of f at the endpoints of this segment. So the conclusion is that then there exists a C in the segment such that fb minus fa is the derivative for single variable functions is replaced by the gradient of f at this C. So this is a vector, but fb minus fa is a real numbers. So this vector, from this vector you need to produce a real number, then by taking in the product. So this is the result of the mean value theorem. This is a very elegant, compact form. Right? And you can compare this formula with the corresponding result for single variable functions. They are very similar. If you write this in components form, component-wise, this equality becomes fb minus fa equals the scalar product or inner product of two vectors is the sum of their multiplication. If it's the sum of the multiplication of the corresponding components of the vector, that is So this is the ith component of the gradient of fxc. Well, bi minus ai is the ith component of the vector b minus a. Okay, so this is the statement of the mean value theorem, very important in our study of multivariable functions. Now we need to prove this theorem. The proof of this theorem illustrates a very useful idea. That is, when we encounter a multivariable function, we will try to transform the function into a single variable function. How to do this? So the idea is very simple. This is L. L is b minus a. For simplicity, we denote b minus a by L. Then from our function f, we can construct a new function phi divided on the 0, 1 interval. Phi t is f a plus tl. You see, when t runs in the interval 0, 1, a plus tl is a point in the segment. Therefore, a plus tl is contained in the domain of definition of f omega, because we assume that our assumption is that the segment AB contained in omega. This is a condition where our theorem could apply. Okay. Therefore, because of this condition, we can define this function phi. And now phi is a single variable function, and we applied the null result of single variable function to this phi. Well, if our A is here, our B is here, then the segment joining A and B, there are some part of this segment lies outside our omega. Okay, therefore, in this case, we could not define this function phi. But I will tell you, although the following proof is not applicable to this situation. Okay, this is the reason why we need to assume that the segment AB contained in omega. Okay. Now with using this idea, we prove this important theorem. So as before, let L to be b minus a, and consider this function phi, which is well defined in the 0, 1 interval. Phi t is f a plus tl. Because L is b minus a, so this is f a plus t b minus a. Okay. Then because f is differentiable. Okay. Since f is differentiable, we see that phi is differentiable. On this closed interval. Why? Because for any t in this interval, we want to see that the derivative exists, but the derivative is the limit of s goes to 0, phi t plus s minus phi t divided by s. But what's this? This is the limit of s goes to 0. Phi f plus s is phi t plus s is f a plus t plus sl. Okay. The t here replaced by t plus s by the definition of phi. Okay, so then minus phi t is f a plus tl, then divided by s. But this is s goes to 0, f a plus tl plus sl minus f a plus tl divided by s. What's this? This is exactly the directional derivative of f at the point a plus tl along the direction l. Okay, so this a plus tl here and here serve as the a in the definition of directional derivative. So compare the definition of directional derivative, you will understand this equality. So this is by the definition of directional derivative. Okay, so this result we will use later. Very important. Such a function phi, the derivative of phi at any point t, as long as it is defined, equals this directional derivative. In our previous discussion of directional derivative, we consider the directional derivative of f at the point A in the direction L. That is t equal to 0. But now we need to consider different t. So we have another analyze this in detail from this several steps. I hope that you can understand this. Okay. Now having verified that phi is differentiable and compute the derivative of this phi, we can apply the Lagrange theorem for single variable function to this phi. Okay, so by Lagrange, our fb minus fa. Fb is exactly phi 1, while fa is exactly phi b, phi 0. Remember, our phi t is f a plus tl, and the l is b minus a. Therefore, it is easy to see that fb minus fa is exactly phi 1 minus phi 0. So the multivariable function problem is converted into a problem about single variable function phi. Now we apply the Lagrange mean value theorem to this phi. This will be phi prime tau 1 minus 0 for some tau in the open interval 0, 1. But the derivative of phi we just computed in the last page, which is f, the directional derivative of f along the direction L at the point a plus tau L. Okay, this here in this step we apply our this computation. Okay, so now by our relation between directional derivative and the gradient, this is actually the gradient of f at the point a plus tau L in the product of which L is b minus a, so we can replace this L by b minus a. So let Xi be the point a plus tau L, which is a point because tau is between 0 and 1. This is a point in the segment AB. Therefore, FB minus FA equals the gradient of F at this C inner product which B minus A. So this proves our mean value theorem for multivariable functions. Okay, so this is a very important theorem.